In this video, I'll show you how I overcame Godot's 16 lights per object limit with my custom 2D light system to achieve this effect. Godot's 2D light system has a limit of 16 lights per object, so any light beyond the limit will not render and show up as a dark area. In games like mine, where players can place lighting objects dynamically during gameplay, this limit can be quite restricting. I've been trying to find a way to overcome this limit. In Godot's official documentation, they suggest using additive sprites to replace lights, but this method doesn't work well in dark areas. My ideal lighting system should support an unlimited number of lights with scalable performance, work in dark areas, is not overly bright when lights overlap, and it doesn't need to support shadows. After some online research, I couldn't find a solution that fits my needs. So I implemented a custom lighting system for my game. It can support an unlimited number of lights with good performance. It works in dark areas and is not overly bright when lights overlap. And each light can be adjusted to different sizes, colors, and intensities. My lighting system works by rendering a lighting texture in a separate sub-viewport. This texture has the same size as the game's main viewport and tells us the color and intensity of the light at each pixel on the screen. This lighting texture is combined with the game's screen texture using a shader to create the final lighting effect. To generate the lighting texture in the sub-viewport, I use lighting sources and lighting sprites. Each lighting source contains information about a light source, including global position, size, color, and intensity. It can be added to any game object that emits light. Each lighting source is associated with a lighting sprite, which is a Sprite 2D node that's a child of the sub-viewport. Lighting sprites are responsible for drawing light textures onto the sub-viewport using information from its lighting source. To create the final lighting effect, I use a shader to blend the lighting texture with the game's screen texture. The shader takes in the environment's darkness color to darken each pixel on the screen. Then, it restores the original screen color based on the light color and intensity at each pixel. Here's how I set up this lighting system in my project. I have a lighting sub-viewport scene with update mode set to always, transparent backgrounds enabled, and handle input locally disabled. The sub-viewport has a child 2D node that will hold all the lighting sprites in the game. The sub-viewport has a script for managing lighting sprites, including functions for assigning or releasing a lighting sprite when requested by a lighting source. To optimize for performance, I pre-allocate a pool of lighting sprites instead of dynamically allocating and freeing them on each request. The lighting sub-viewport is placed inside my game world scene. I also have a lighting sprite scene, which is a Sprite 2D node with a radial 2D gradient texture, but you can customize this with your own texture as well. The lighting sprite has a material with a mix blend mode. Additive blending also works and will result in brighter lights, but I prefer the mix mode a bit more. The lighting sprite has a script that keeps a reference to its associated lighting source. It also has functions for updating the lighting sprite's size, intensity, and color. To turn a light on or off, I simply show or hide its lighting sprite. Next, I have a lighting source scene, which is simply a node 2D. It has a script with export variables like size, color, and intensity. On ready, the lighting source requests a lighting sprite from the sub-viewport, and on exit, it releases the lighting sprite back to the pool. It also has helper functions like turning the light on or off and changing the color of the light. I add lighting sources to all the light objects in my game, such as this garden light. To generate the correct lighting texture in the sub-viewport for the current screen, I update each lighting sprite's global position to match its lighting source's global position. I handle this inside the sub-viewport's process function, instead of adding a process function to the lighting sprite script to minimize function calls. From my experience, minimizing the number of process functions can help a lot with performance. In the sub-viewport's process function, I also update the sub-viewport's canvas transform to match with the main viewport. My sub-viewport also listens to the main viewport's size changed signal to update its size accordingly. Finally, I have a daylight color scene, which is a Sprite 2D node that holds my lighting shader. I place this scene in my game world, where I have the lighting sub-viewport. In my game world's ready function, I set up the sprite's texture to be the Sub-Viewport's texture, so I can access the lighting texture in the shader. This needs to be done in the script instead of the editor to avoid a Godot engine bug, which I added a link to in the descriptions below. The daylight color sprite has a script that stores a reference to my game camera. In the process function, I set its global position to the camera's screen center position to align the Sub-Viewport texture on the sprite with the game's screen texture. I attached the lighting shader to this sprite. The shader has a parameter called darken color, which is the darkness color of the environment, similar to the color that you set on a canvas modulate node. This parameter is updated in my script based on the time inside the game. In the fragment function of the shader, I read the color from the screen texture and the color from the light texture. I compute the darkened color of the screen, then calculate and add the lighting effect using the light's color and intensity. For my game, I want lights to cancel out the darkness color but never exceed the original color of the scene. But you can modify the shader if you want different effects. My game has multiple screen reading shaders, so I added a back buffer copy node as the parent of my daylight color sprite, with this copy mode set to viewport, so my lighting shader can always read the up-to-date screen texture. If you want to read more about why this is needed, I added a link to Godot's documentation in the descriptions below. My daylight color sprite and its back buffer copy node have a large z-index of 1024, because I want my lighting shader to be applied to all objects with a lower index, and anything drawn above the lighting sprite will not be affected by the shader. And that's it for my custom 2D light system. I hope this video was helpful, and I love to hear how you handle lighting in your games. For a quick progress update on my game, I started working on building construction and farm animals before I redesigned my lighting system, so I'll continue to work on them next, and I'll see you in the next video.